Welcome back to CodeChef. Imagine a task where the solution to a big problem depends on solving a smaller, identical version of that same problem. This seemingly mind-bending concept is called recursion. Today, we're going to demystify recursion, breaking down how functions can call themselves to solve complex problems elegantly. The best way to understand recursion is to think about a set of Russian nesting dolls. Each doll contains a smaller version of itself until you reach the tiny innermost doll. To open the largest doll, you eventually need to open all the smaller ones inside. In programming, a recursive function is like this. It calls itself to solve a smaller part of the problem until it reaches a base case, that smallest doll, which it can solve directly. Then it unwinds, building up the solution layer by layer. In this tutorial, you will master these key concepts: what recursion is, the importance of a base case, how recursive calls break down problems, and examples of common recursive problems. Recursion is a programming technique where a function calls itself to solve a problem. Every recursive function must have two main parts: a base case. This is the simplest possible input for which the function can return an answer directly without making any further recursive calls. It's crucial because it stops the recursion. A recursive step. This is where the function calls itself with a modified, usually smaller input, moving closer to the base case. Without a proper base case, recursion would run forever, leading to an infinite loop. Let's look at a classic example. Calculating the factorial of a number. The factorial of 4, written as 4 exclamation mark, is 4 times 3 times 2 times 1, 1. Notice how 4 factorial is also 4 times 3 factorial, which is 4 times the factorial of a smaller number. Here, our base case is when n is 0 or 1, returning 1. For any other number, the recursive step multiplies n by the factorial of n minus 1. Let's trace factorial 4. Factorial 4 calls 4 times. Factorial 3 calls 3 times factorial 2. Factorial 2 calls 2 times factorial 1. Factorial 1 hits the base case and returns 1. Then it unwinds. 2 times 1 returns 2. 3 times 2 returns 6. Finally, 4 times 6 returns 24. Recursion is used in many advanced programming problems. File system traversal. Finding files in nested folders is a recursive problem. A folder can contain more folders. Sorting algorithms. Algorithms like merge sort break a list into halves, sort each half, and then combine them. Fractals. Generating complex, self-similar patterns in computer graphics is inherently recursive. While not always the most efficient, recursion offers an elegant and often intuitive solution for problems that exhibit this self-similar structure. Here is a classic example of recursion in action: calculating a factorial. First, we define our function factorial and its base case. This is our stop condition, where if n is 0 or 1, the function simply returns 1. If the number is not 0 or 1, we move to the recursive step. The function multiplies n by the result of calling itself with a number 1 less. This process repeats until it reaches the base case. As you can see, when we input 5, the function correctly calculates and prints the factorial, which is 120. Today, we learned the basics of recursion: a function calling itself, the critical base case to stop the recursion, the recursive step to move closer to the base case. Recursion is a powerful concept that helps you think about problems differently. It's challenging but incredibly rewarding to master. Keep practicing, and I'll see you in the next lesson.